Hi class, welcome back. Today we're going to discuss antiderivative and indefinite integrations. So first of all, what is an antiderivative? Well, anti means the opposite, right, of a derivative. So as we move forward, you guys will see that the antiderivative, it's sort of like a process, like just like the derivative is a process. Finding the rate of change of a function. Well, the antiderivative, what it's going to do is going to go from the derivative, and you're going to be able to get back to the original function. So it's sort of undoing the derivative, right? So it's undoing derivative. So from the derivative, you have the original function, and then you took the derivative, you got to the derivative function. The antiderivative will be able to get the derivative function and undo the derivative to be able to get to the original function. And then so we're going to use also a synonym, which for this is also an indefinite integration. So now we're going to discover that process, that technique of doing the antiderivative in the first examples. And then we're going to sort of do a few examples at the end of this section. All right, so the objectives are to write the general solution of a differential equation and use indefinite integral notation for antiderivative. Use basic integration rules to find antiderivative, and then find particular solution of a differential equation. So there's a whole field known as differential equations, where you actually have to find the solution of the equation. So we'll touch base a little bit in this section, but so the point here is to find a function f whose derivative is given here. So let's say you want to find the original function, and this is the actual derivative of this. Then you might want to use your knowledge of derivatives to conclude that if you're given this, if you can guess that, hey, if the original function was x cubed, then that was because if you take the derivative of this gives you 3x squared. So it's sort of kind of like going backwards, right? If you have 3x squared, we know that when you're doing the derivative, what do? We bring down the power. So in this process, we have to bring down the power and subtract 1. So let's try a few examples here of trying to find the antiderivative of the derivative, right? So if this is a derivative, can you guess what was the original problem? Well, what we should do is that this what we have to do is usually we take a function, and since this has the power 1, we tend to do decrease the power by 1, right? And so this becomes the factor over here, and then we subtract 1. So it seems like the original function would have been x squared. The original function for this one, well, if you have the original function to get x, then you probably have to have an x squared, and then to bring it down, and then subtract 1. But then you have to divide by 2 to compensate for the fact that this is just 1. So if you notice, 2, if you do the derivative of this, it will be 2x over 2, which gives you x. If you guys work backwards in this one as well, the original function from this derivative will be x cubed over 3, because you take the derivative of this will be 3x squared over 3. The 3's will cancel, you'll get the x squared. For this one, if you think about it, negative 1 over x, you will have to bring the denominator to be x to negative 1, and then do the derivative of that, which be bring down the power, which is negative 1 times negative 1 becomes positive, and then subtract 1, which gives you negative x to negative 2. And then you bring down the power, and that's how you got this one. Same thing, same argument over here. You will have negative 1 over 2x squared. You bring this up, take the derivative, you bring down the negative 2, and multiply here. Negative 2 times negative will become positive 2, and then we'll cancel with this one. And then you have, and you subtract 1 from the power, so from negative 2 minus 1 will become negative 3. And so x to the negative 3 will turn into 1 over x cubed. And the derivative of sine is cosine. So there is sort of like a technique that we're doing here. So it seems like it seems like what we're doing here, if we play around with the process, let's think about this. When we took the derivative of a function using power rule, derivative, the power rule suggested that we multiply by the power. That was number one. And number two was to reduce the power by 1. Right? That was the derivative process for power rule. Well, for the antiderivative, of the power rule, it seems like we're doing just the opposite. If so, it seems like all we're doing, so for derivative we went this way. So it seems like for the antiderivative we'll be doing this. So we'll be doing the opposite, right? So instead of reducing, if you guys think about this, instead of reducing, you're going to add a power. Add 1 to the power. And then instead of multiplying by the power, we're going to do the opposite of multiplication, which is divide by power, by the new power, right? So I hope that kind of makes sense, right? In one you were reducing, so that means you were subtracting the power by 1. But in this one you're going to add 1 to the power, and then that new power is going to be used to divide by the new power, right? So you're going to divide the function by the new power. So let's see if that helped right here, right? So if you have here, if you're trying to if you have this and you're trying to get to here, then what are we going to do? According to this problem says, now we know that we just got to add 1 and then divide by the new power, which is the new power is 2 plus 1, right? Which is 3. So if you guys notice, what we end up getting, right? What we end up getting is the original function, which is those cancel each other out, and then will give us plus 1, right? So we're gonna sharpen our process here, but you see what happens here is, notice on this problem, what are we doing here? If you're going from the derivative to the original function, you're doing the antiderivative, so add 1. So you have a 1 here, so 1 plus 1 is 2. And then divide by the new power, so divide by 2, and that will eliminate that one. What about this one? Add 1 to the power. 1 plus 1 is 2, and then divide by the new power. Add 1 to the power, so that's a 3, and divide by new power, and so on and so on, right? So we'll formalize this over and over again. Now there is one thing that we have to consider here, so we have to be careful. We have to actually extend this a little bit further. So I hope the following is going to make more sense. So if this is the original function, and do you notice that any of these 3 functions will actually give us the same derivative, right? If you guys take the derivative of this will be 3x squared. If you take the derivative of this, it will be 3x squared, and then this is 0. If you take the derivative of this is 3x squared, and this will be 0. So either way, any of these 3 functions will give us the same derivative. So the question is, if you're trying to find the original function from this derivative function, how do we know that it's not this one or this one or this one? How do we know? How is it possible to know that which one it is going to be? Well, we don't know. We're not going to know. So when we are trying to find the original function, we won't know whether the original function had a constant added to it. So what we're going to do here is we're going to compensate for that. So when we do the antiderivative of a function, we're always going to add a c, a constant, right? When we find the antiderivative, we're going to add a constant. Now there will be occasions actually where we actually can find the c, but we need to know a little more about the original function. So if function f is the antiderivative of f on the interval I when f prime of x is equal to f of x for all x. And so we want to add this c at the end, right? And so what we're saying here is that when we apply the antiderivative, we're sort of creating a family of functions. Why? Because this function, these three functions are different, right? But they give us the same derivative, but they're only different by a constant. And so they're different, but they're only different by a constant. So therefore, we can say that they're part of the same family of the same function, right? They're only different by a constant, so they're part of the same family. So we're always going to add this c at the end when we're finding the derivative, the antiderivative of a function. All right, there's a whole field of mathematics that's known as differential equation, where we ask to find the original function. So you're given an equation with derivatives, and we need to find the actual original y value. So for example here, if I ask you to find the general solution of the differential equation because it has to do with derivative of y prime equals 2, So our goal is to find the original equation, the original y. So what we're going to do here is we're going to apply the antiderivative to this. Well, if your slope is 2, that means that this came from the original function y equals 2x. But this could be actually not just the only solution, but we can also have 2x plus c. So what we're saying is, if we look at the picture over here, any of these lines have a slope of 2. So therefore, any of these lines, any of these equations will satisfy this equation. Hence, any of these equations are solutions to this equation. So let me say that again, right? And we're not going to do too much of this. You guys will do maybe this in the other calculus courses, but definitely in differential equation class. But what we're saying here is, if I ask you to find the original function of this equation, the solution of this is the original function, right? Is the original function. So you're looking for the original function that satisfies this equation. And so we found it, right? This is it. This is the general solution. All right. So that's one application of the antiderivative. We're going to extend this further, and we're actually going to introduce some notation. When we apply the antiderivative, instead of how we have prime for the derivative, for the antiderivative, we're going to be using this symbol right here, right there. This symbol is the integral symbol, the integral sign. And what this is saying is, you're taking the antiderivative of f of x. Now there is, so this is called the integrand, where you're taking the antiderivative of. And then this part over here, it's important, it is part of the notation, so we have to add it. It is the variable of integration. This tells us in what respect are we taking the antiderivative from. So in this case, we're doing this in respect to x. So this could be in terms of t, in terms of y, in terms of delta, and so it just depends on the function. So this is telling us in respect which variable we're doing this. And then once we apply the antiderivative of this, once you apply the process of the antiderivative, we're gonna get the new function, which is the antiderivative of f of x, and then we automatically gonna add the c. Now, this is known as the indefinite integration or the antidifferentiation. It is called indefinite integration because later on we're actually going to be able to plug in some numbers in here, and that's going to be known as definite integral. So right now, the indefinite integral, the indefinite integration, is the one without numbers in here, and we always have to add the c for this. So indefinite integration. All right. So the indefinite integral is read as the antiderivative. So we read this as the antiderivative of f of x of f with respect to x. So we read this that way. And the indefinite integral is a synonym for antiderivative. So it's very common for us to go back and forth by saying integral and saying indefinite integral, right? Or saying antiderivative. So they all mean the same thing. And personally, I'm gonna go back and forth without even thinking. So because we are so used to saying it both ways, then I'm just gonna you guys will hear me saying it in two different ways all the time, and this is my subconscious, right? And that's because it's normal for us to say it like that, and in either way. All right, so what we're saying here is let's go back to the principle of the antiderivative. What we're saying is that if you have a derivative inside, right? If you have the derivative inside, so when you apply the antiderivative to a derivative function, we can think about it exactly as you undoing the derivative of this. So that means you're gonna cancel the derivative with the antiderivative. They're gonna cancel and just give you the original function f of x. Now obviously you have to add the c there, right? Because you took the antiderivative. And then in addition, we can use this in a different way by saying, well, if f of x is the derivative function and you're taking the antiderivative of this, well, what we're going to say here is, well, if you apply the derivative to the antiderivative, let me say that again. You see the order? Here you're applying the antiderivative to the derivative. Here you're doing the derivative to the antiderivative. Well, again, because those are inverse of each other, they're going to undo each other. So the derivative, the antiderivative will cancel each other out, and you're just going to be left with f of x. Now, notice, it kind of makes sense why this does not have a plus c. Can you guys think about that? Why this does not have a plus c? Well, because this one, if you guys think about this has the plus c, right? When you do the antiderivative of this, whatever that is going to be, let me just say that. Let me just say that this is going to be, this right here is going to be f of x plus c, right? Because that's the antiderivative of f of x. But then you're taking the derivative of this. And what happens when you take the derivative of this? Well, the derivative of this is going to be f of x. And the derivative of a constant is 0. So you guys see in this case, in this order, there's no c. I hope that kind of makes sense. All right. So we have found a value for the antiderivative, right? Why? Because as it's important for us to be able to find the rate of change of a function, is equally important for us to actually, if we're given the rate of change, to find the original function. And we have so many application problems where we can use that. But as we've seen before, the original functions and the inverse functions are very important because they cancel each other out, and we can apply this in many ways to solve equations. Well, we can use also similar to any application like this, right, with the antiderivative. So let's jump into some rules. So it's important for us. I highly recommend you guys to put this, write it out on your own in a piece of paper. This summarizes all the derivatives that we've seen so far. And I want you guys to also write this in a piece of paper. And then please have this where you guys can see this over and over again. This is what I would have done, right? If I were you. So we know what happens with the derivatives, right? These are the derivatives you guys already know. Derivative of a constant is 0. The derivative of kx is k. The derivative of k times a function is k times f prime. The derivative of the sum of functions is the derivative of independent functions, right? The derivative of the power rule is the power rule, right? And so on and so on and so on, right? Well, what we're saying here is you can use this to come up with that. you can use this to come up with that. You can use this to come up with that. And let me show you guys what I mean by that. And I'm not going to do all of them, but I'll show you guys how these give you this, right? So if I have d over dx of c equals to 0, then I'll do the technique that we talked about on top, right? And I'll take the antiderivative of the left side and the antiderivative of the right side, right? Because if I do if I do it on the left side, I have to do it to the right side. So what happens with these two? They cancel each other out, and now we have c equals to the antiderivative of 0 dx. And do you see? That's how we got that one. Kind of cool, right? Should we try another one? Let's try this one now. So let's figure out how this gives us that one. So again, we'll do the same thing. We'll write derivative of kx equals k. Then I'll take the derivative, the antiderivative of the left. So if I do it to the left, I have to do it to the right, just like to maintain the same value of the equation, right? What happens with these two? They cancel each other out, right? And then according to the order above, we're gonna have the same result, but we're gonna add a c, right? And this will give us the antiderivative of k. Do you guys see that? You remember that because the order is antiderivative derivative, we're always gonna add a c. And I encourage you guys to try the other ones, right? And I'm just gonna go ahead and do. I'm gonna go ahead and if you guys notice, not all of them work that way, right? They don't work all like that, right? But we can argue how they're helpful, right? We already talked about the power rule. For the power rule, we do the opposite, right? To do the antiderivative of a power rule, what we do is we add 1 first to the power, right? And then whatever that power is, we're going to use that to divide the whole thing, and then add the c. These ones are sort of kind of, we can follow these ones the same way that we did before. So so to be honest, I don't think I memorized this ever. I memorized these, and then I use this to come up with those, right? When I was a student, that's what I did. I couldn't memorize too many things, so that was my process of going around it. So let me show you guys one of them here. So the derivative of sine is equal to cosine of x, right? We already know that. We already spent so much time trying to memorize this, right? If we take the derivative of this, we have to do antiderivative. Sorry, if we take the antiderivative of this, we have to put the notation of dx. Don't forget that. I know it's gonna be something you guys will forget, but try your best to write it. You have to get used to that. And then so what we're gonna have here is the antiderivative of this will cancel each other out, giving us sine of x. And because of the order, we're gonna have to add a c, and this will give us the antiderivative of a cosine. And you see, there you go. All right. So I hope that you guys spend some time trying these on your own. I'm gonna clean this up because I don't. When I make this available, I don't want this to be sort of there. Just in case if you guys want to take a picture of this. All right. So let's try another problem here. We're gonna use the antiderivative for power rule, right? So what are we going to do is I recognize that there's a power of 1 in here, right? There's a power of 1. So when I take this, I have to use power rule for antiderivative. And so what I'm going to do is I'm going to add 1, and maybe I can be more obvious here. If you guys want to, I can make it more obvious. Oops. If you guys needed to see this for this time, it'll be 1 plus 1, and then I'll do it this time just so you guys can kind of see it, and then over 2, right? So this new power is the same power over here, right? So the order matters, right? You first gotta add 1 to the power, then you use that power to divide the entire thing, and then plus c. That's another thing you guys will probably remember, forget. So, and I'll take off points in the test if you guys forget your c. I promise you, I will take off points. I have to take off points because you're not giving me the right answer. So you have to make sure you get used to adding the c into the problem. All right. All right. So then that's that. So we can simplify this now, right? This is x squared. This is x squared. 3 over 2, and we're just gonna leave it like that, right? That's your answer. So don't need to memorize it. You just have to think about that you're just doing the reverse order of the derivative. Here are a few more examples for us to try. A lot of times, just like we did it for the derivative, we actually have to set up the antiderivative so that we can use one of the rules. I remind you guys that all the rules that we have so far for the antiderivative, none of one has to do with the quotient. If you guys want to go back and check that out, if you guys notice, what I'm doing here is I'm moving this to the top, and I have negative power. That's fine. For this one, I'm changing that to a power form, just like what we do it for the derivative. And then for this one, because it's a constant, we're allowed to move it to the outside, right? And I think there was the rule would specify, one of them specify that we can do that. You guys see that over here? If you have a constant, you can move that constant outside. When you have an antiderivative of a sum, you can do it independently of each other, and so on, right? So you can move the constant outside, so you can just focus on this part so far, right? And so if you guys notice, what I'm doing here is I'm adding 1 to negative 3. So negative 3 plus 1, they will undo each other, and that will give you negative 2. The new power is the new power we're going to use to divide, plus c. So what about this one? 1/2 plus 1 gives you 3/2. So divided by and then use that to divide the whole thing. 3/2 plus c. The antiderivative of sine is negative cosine of x, and then we add the c. But then we can so that's your integral. Technically, this is your answer, but we can simplify further. We can put the minus in front of it, and we can drag this to the denominator by changing the sign. That will give us negative 1 over 2x squared plus c. Remember, you gotta keep your c. This one is if you guys notice, when you divide by a fraction, I remind you guys that you pretty much what you're doing is multiplying by the reciprocal of this. What's the reciprocal of 3/2? Is 2/3. So this, it turns into a product by flipping it, right? 2/3. 2/3 times x to 3/2 plus c. This is just algebra, this step. And then here we can just multiply these together, and that gives negative 2 cosine plus c. Now be careful here, please. Be careful, please. When you're doing this, remember that this is multiplication, so this is gonna multiply whatever you get here. That's why I put it in parentheses to make it clear. All right, so next one. Right. So the next one, we have technically a 1 in here, right? I have a 1 in there. You guys don't see it, but there's a 1 there, right? Even if there's nothing there, we assume that there's always a 1, a multiple of 1. And the antiderivative of 1 is technically we just add the x. So let me maybe add some color here. When you have a constant by itself, you just add the x, right? You guys remember that rule? It's up here. When you have a constant by itself, the antiderivative of the constant is just add the x. Just like backwards, right? When you have the derivative of kx is k. Well, if you go backwards, that will give us, you're just adding the x. All right, so 1 times x plus c. Perfect. What about this one? Well, in this case, now we have x plus 2. So the way we're going to do this is by doing one term at a time. So there's a power 1 there. So what are we going to do? We're going to add 1. So 1 plus 1 is 2, divided by a new power. Plus 2, and there's a imaginary, so that's a constant. So the derivative of a constant, remember that we add to it, right? So we're going to add the x, followed by a plus c. Remember that, think about this. Derivatives takes away power, right? Subtracts power. The antiderivative adds power, right? Adds to the power. So you're adding onto it. So here's another one. Notice that there's 3 terms. We're going to do one term at a time, right? One term at a time. So the antiderivative of this, what do we do to the power? We add 1, divide by a new power. Do you see what I did to the 3? Nothing, right? I just carry over the 3, the constant. And I added to the power and divide by a new power. Followed by the next one, negative 5x, right? So we look at the power of the x, and we add 1 and divide by a new power. Followed by the plus, followed by the x, right? This has a power 1. The x has a power 1, so we're going to add 1 to the power and then divide by a new power, plus c. All right, and then we'll do the same thing for the next one. So we have a few more to practice. So for the next one, it seems very complicated. It seems like there's a quotient here. Well, again, we don't actually have anything that has to do with a quotient in our rules. So we have to be creative. What I mean by creative is be creative in the algebra perspective. So we know that this obviously has to be written as a power form. And then what we can do here is we have multiple terms on the numerator. So we actually can divide the numerator by this denominator. So we're going to have x over x to the 1/2 plus 1 over x to the 1/2. And then we can simplify these two by subtracting the powers and then moving this to the top. Now remember that I haven't done the antiderivative, so it's very important for me to carry the notation, right? Because I haven't done anything with the antiderivative. Now that it is ready for me to take the antiderivative and I can use one of the rules, then I can add 1 to 1/2. So 1/2 plus 1 is going to be 3/2 over the new power plus x, and then add 1 to the negative 1/2. So negative 1/2 plus 1 is 1/2 divided by the new power plus c. Now, when you guys are adding fractions, right? When you're adding 1 to the fraction, if you guys are not too comfortable, you can use your calculator, right? For now, but please note that you should be trying to get more comfortable with your fractions, so that you can do this more efficiently, right? Then we're gonna simplify, right? We need to go ahead and simplify. We know we're dividing by a fraction, so we're gonna multiply by its reciprocal. So 3/2, the reciprocal of that is 2/3. So multiply that by 2/3. This is 1/2, so multiply by the reciprocal of 1/2, which is 2 over 1. And that's that right there, plus c. And then the other thing is we started with radicals, we finished with radicals. So we're going to go back and rewrite these as square roots with cube power and then a square root over here as well. Now this one is actually interesting, right? This requires very much a lot of creativity. But again, think about this. We don't have an actual rule where you're dividing functions, right? So maybe if we try to think about one of the rules that we have up there, which has to do with secant and tangent, and if we think about it, like there's nothing that has a product but these two. So the way I was motivated to do this problem was, well, what about if I try to get one of those secants or tangents or cotangents, right? Or cosecants, right? So I noticed I had an extra cosine on the bottom, so I separated it into by products, right? 1 over cosine and then sine over cosine. I noticed that this was a tangent, and then I noticed this was a secant, and one of the rules says that the antiderivative of secant tangent is secant. So I was able to use that rule over there. So you guys see my train of thought? All right, so let's try a few more. And I keep doing this for you guys. I put the red part as being I'm applying the antiderivative. So first of all, you have a square root here, so we gotta write it as power form. So the antiderivative of 2 times x to the negative 1/2 dx. The 2 can be moved outside. We didn't have to, but I did. And then now I have x to the negative 1/2. So what do? We add to the antiderivative of this is we add 1 to negative 1/2 plus 1 is 1/2. And divide by a new power, right? So the x stays the same as always. The 2 is being multiplied, and then we add the c. And then multiply by the reciprocal of this, which is 2 over 1. So 2 over 1 times 2 is 2. Turn this into a square root, and there you go, plus c. So this gives us this answer. Let's try the next one. This one doesn't need too much thinking, right? We can do this as we see it. The antiderivative of this in respect to t. What do? I ended up separating these two, but we don't have to. I want to make sure that you guys know that this can be separated, but you guys don't have to. You can just do one at a time. So the antiderivative of t squared, what do? We look at the square and we add 1 divided by a new power, plus 1 and then a constant. What do to the constant? We just add the t as a product, followed by plus c, and there you go. For this one, if you guys notice, another quotient. So what do? We simplify, right? So we're gonna separate it into their own terms. So we're gonna have x cubed over x squared, 3 over x squared, and then these simplify to be an x, and these simplify to be 3 times x to the negative 2. Then now we can take the antiderivative. There's a power 1 there. So what we're gonna do to the power 1? We're gonna add 1, so that becomes a 2. Divide by a new power, plus 3x to the negative 2. So what do we do to negative 2? We add 1. But be careful here, because this is where students sometimes make a mistake. You're adding 1, right? You're adding 1. So this does not turn into a negative 3, but instead it turns into a negative 1. So negative 2 plus 1, they undo each other a little bit, and that gives you negative 1. Divide by a new power, plus c. And then I rewrite the problem as x squared over 2 plus minus 3, and then bring down this x because it has negative power, plus c. And this one, I ended up rewriting it as a power, and then over here as x to the 1/3. Then I use distribution, because again, there's no rule that allows us to take the antiderivative of a product in the rules that we have up there. So we're gonna have to distribute. So we have x to the 1/3 times x. What do we do with those? We add powers. X to the 1/3 times negative 4 is negative 4x to the 1/3. And then now that it's ready, if you guys please note, I'm always writing my notation. It is annoying, right? I probably understand that. But you have to know when can you drop the notation of the antiderivative, and when you keep it. And you keep it as long as you're just simplifying the expression inside. And once you apply the rule of the antiderivative, then you're done, right? You can remove the antiderivative symbol. I've seen sometimes students making that silly mistake. They don't recognize when you can drop the antiderivative symbol. So now we're going to be able to drop it because we're going to apply the antiderivative. What do? We add 1 to 4/3, which is 7/3, and then divide by a new power. Minus 4x, add 1 to 1/3, that gives us 4/3 over 4/3 over the new power, plus c. And then we simplify, right? So this will be multiplied by the reciprocal of 7/3, which is 3/7. This turns into dividing 4 and 4. So this actually is going to be not 1/3, but instead it's going to be 3. And so we end up getting this, right? and then plus c. All right, and it looks good. Looks good, and just double checking my work. There you go. Right, awesome. So, all right. So I hope this gave you a good base of the application of the antiderivative. My recommendation, as you guys see through here, is once you apply the antiderivative for one of the terms, continue doing that for everyone, right? Sometimes students mix up notations, and that makes them more confusing for them. All right, so we found the antiderivative, right? And we kept adding that c. Well, let me extend that concept, and we're gonna extend it by introducing what is known as the initial condition for this differential equation. So what we're gonna do is, if I ask you to find the antiderivative of a function, and let's say you did, right? You took the antiderivative of this function, and that gave you x cubed, right? What do? We add 1 divided by a new power, which is divided by 3. Those will cancel each other out. That's how we get the x cubed. Minus 1, which is minus x, plus c, right? So going back to that concept of this this equation, we found the solution, but we're not exactly know the original function, because we don't know what that c is going to be. It could be 0, it could be -1, it could be 5, it could be -27 or 2. So if you guys think about this, what we're saying is that the original function could be one of these, right? And if you guys see, they all behave the same way. They all behave the same way. They are the same function, except that that depends on the c. It will tell them where they are located, right? So now we could, so in a way, the general solution is an infinite solution, right? It has infinite solutions, but we can be actually more specific and actually find one unique solution if we know something particular about the original function, and that's what's going to happen here. So this will give us a particular solution if we're given an initial condition. And in this example, they're going to say, let's say that the original equation passes through the point 2,4. Passes through the point 2,4. Well, what does that mean? Well, this is your x and this is your y. So that means that when you plug in x into the function, to the original function, that will give you 4, right? So if this is your original function, if you plug in 2, 2, 2, this should equal 4. So what's going to happen here is once we plug in the 2 there, we're going to get 2 to the third, which gives us 8, minus 2, plus c, and that equals 4, right? That equals 4. So if you guys notice, this actually, by just doing some simple algebra, we can actually find that if you combine 8 minus 2, that will give us -6, and then subtract both sides, this will give us 6 minus 2, giving us c equals -2. So you're always going to be able to find that value, right? So that gives us a specific value for the original function. So if we're given an initial point, then we can actually find the particular solution, the unique solution of that differential equation. So in this case, that would be this one right there, because it passes through the point 2,4. All right, over here, right? Do you guys see that? That's the only one that passes through the point 2,4. All right, so we can see here that the value of having initial point. All right, so let's try an example here. Let's find a particular solution. Find the general solution first of this derivative function, and then find a particular solution that satisfies the initial condition f of 1 equals 0. So this is what's given. I didn't write it down, so I wrote it down here. So this was the original problem, right? F prime of x equals 1 over x squared. Our goal is to find f of x. So the way we're going to do this is, well, this is given to us, and what I'm going to do is I'm going to undo the derivative by applying the antiderivative on both sides of the equation, right? Kind of makes sense. And then, so this is the same thing as this, right? I just moved that to the top so that we can have a power form. These would cancel each other out, giving us f of c, f of x, sorry, equals to the antiderivative of this. What do? We add 1, so negative 2 plus 1 gives us negative 1, divided by a new power, plus c. And so that tells us, by simplifying this, that we're going to have the negative 1 over x plus c. And then we're going to say, okay, let's note that that they give, so this is the general solution, but they're also giving us a particular solution or an initial condition for us to find the unique solution. So if we utilize f of 1 equals 0, this will imply when you plug in 1 for x, the whole thing is going to equal 0. So plug in 1 for x, so if you have the original, plug in 1, negative 1 over 1, plus c should equal 0, right? Because according to this, it tells us that the f of 1 should equal 0. So then what we're going to do is we're going to solve for c. So this is negative 1 plus c equals 0. If you add 1 on both sides of the equation, then this gives us c equals 1. So we found out that this c is actually equal to 1, and we can finish the problem by putting it all together. So if the original function f of x equals negative 1 over x plus 1 for all x greater than 0. And so so we can see here all the gray lines right there, they are just a family of the solutions, but there's only one solution, right? And that's right here. By giving us that specific point, we are able to narrow it down to the unique solution of the actual function. And there you go. So I hope this makes sense. Again, the whole point, what I want you guys to think about this, at least get from this section, is the notion that we now know a process known as the antiderivative. And the antiderivative with the derivative will undo each other, right? All right, so please let me know if you have any questions. I'll see you guys next time.